Today I'll be talking about improper coloring graphs on surfaces. So as you can see, there are many other people I've written down here. So this is not a talk about one result, it's a talk about how I got into the topic and how the problem progressed and how it ended up here. So the first half is something that's been done in the past 2, 3, maybe 4 years, and the latter half is what I've been doing in the past 2, 3 months. So this is joint work. The talk is based on joint work with Andre Raspo, students here at KAIST, Hojin Jisoo and Kiwon, and some other French people, Louis Esperet, François Dros, and Michael Montassier and Pascal Auchem. So first I'll start with preliminaries, some basics. So a graph is k-colorable if we can do the following things, right? First one is for each vertex you assign a color from 1 to k, and the second is every edge. If you look at every edge, the color on the two endpoints are different. So this is just proper coloring. But there's a different way you can view this. So a way you can view this is you're partitioning the vertex set of your given graph into k parts, because we want to do a k coloring. And then we say each part induces a graph of maximum degree at most 0. So it's an independent set. So in a proper coloring, each color class is an independent set, so the maximum degree is 0, or at most 0. So if you look at the 5 cycle, the 5 cycle is 3 colorable, and you cannot color it with 2 colors. But what we're going to do is maybe this condition is too strong. Maybe you want to do something similar, but you want to relax this condition on coloring. So we're going to relax the condition in this way. Namely, we're going to say a graph is D1 up to dk colorable if there's a partition satisfying the two things. So the first thing is you want to partition the vertex set, right? So this is the same as your classical k coloring. So if you can partition the vertex set into the same k parts, but now instead of requiring each part having maximum degree at most 0, you're going to allow some defects, or you're going to allow some edges that are monochromatic, right? So the ith part is going to have maximum degree at most d sub I for every I between 1 and k, right? So what this is saying is maybe this condition on the maximum degree at most 0, right? So instead of having each part being an independent set, you're going to allow some vertices to have some neighbors of the same color, right? So this is weaker than the k coloring. But what this allows is that now this 5 cycle, you can partition into 2 parts such that one part induces a independent set, so the maximum degree is 0, but the other part is going to have a maximum degree at most 1, right? So somehow, if you look at this odd cycle, every odd cycle of arbitrary long length, you cannot color it with 2 colors, but you can always color it with 3 colors. But somehow this is too much of a jump, right? You want to try to see what's happening if you relax this condition. So every odd cycle, as you can see in this picture here, you can partition it into 2 parts such that one part is an independent set, and the other part is almost independent except for that one monochromatic edge, right? So this is the definition we're going to stick with today. And because the title is Improper Coloring Graphs on Surfaces, I'm going to explain what a surface is. So a surface is a non-null, compact, connected two-manifold without boundary. But whenever I see that definition, I don't like it because it's too continuous, right? I don't like anything that involves this manifold and this compactness. So I'm going to describe a surface in a combinatorial way, right? And in order to explain what a surface is in a combinatorial way, I'm going to introduce 2 combinatorial operations, or 2 combinatorial objects. One is this handle here. So this is one picture, and so these are the same pictures, right? So you can imagine this handle being represented as 2 circles where the circles are in opposite orientation. And the other object is this cross cap, right? And this cross cap has some fixed orientation. So we say as an orientable surface is you start with a sphere and you add some non-negative number of handles to the sphere. And we say a non-orientable surface is something obtained by starting with the sphere and then adding some positive number of crosscaps. So what does this mean? So why is this called an orientable surface? Because it's orientable because you know if you're inside the surface or outside the surface. There's some clear boundary, right? So if you're on a sphere, you know if you're outside or inside. You know if you're standing on a sphere, if you're standing up or if you're standing down. But if you look at this non-orientable surface, then there's no such thing. It's like the Mobius band where it's all one surface or one plane or something like this, right? So there's no up and down on this surface. So you have no such thing called an orientation, which is why it's called a non-orientable surface. So why do I introduce this notion? I said I was going to explain what a surface is, but now I have two other objects. I have an orientable surface and a non-orientable surface. So the reason I explained this, or I defined this, is because there's this big theorem called the classification of surfaces, right? So a surface, so all this classification of surface theorem says is that a surface is either orientable or non-orientable. And this may sound trivial by these words, but what this actually represents is if you start with some sphere, and if you add 3 handles and 2 crosscaps, then it's going to fall into one of these two categories. It's going to be either orientable or non-orientable. Even though the definition says that an orientable surface is you start with a sphere and you add some number of handles, and a non-orientable surface says you start with a sphere and you add some number of crosscaps. So why is this? It's because there's this lemma that says adding 1 handle or 1 crosscap is the same thing as adding 3 crosscaps. And this is some illustration on why this is true, right? So I have these pictures. So this is what is this? This is 2 crosscaps, and if you follow the diagram, I can create something that's called a cross handle. And this diagram here is saying a cross handle is the same as a handle if you have 1 more crosscap, right? So all this lemma is saying is if you have 1 handle and 1 crosscap, this is the same thing as 3 crosscaps. So this lemma basically solves this problem. So if you give me some surface with some number of handles and some number of crosscaps, what I'll do is I'll say if you have some crosscap, I will transform all the handles into 2 crosscaps, right? Because this is what this lemma is saying. So you can destroy all the handles and create a surface with only crosscaps. And now you fall in the realm of this non-orientable surface. But if you have no crosscaps, you only have handles. And at this point, you're an orientable surface. So this lemma basically solved this. But the one important detail is that you might say 1 handle and 1 crosscap. Since 1 handle and 1 crosscap is equal to 3 crosscaps, as a mathematician, maybe you want to cancel these 1 crosscaps and say 1 handle is equal to 2 crosscaps. But this is not true because if you add 1 handle, that surface will be orientable. So this is your torus. But if you only have 2 crosscaps, then you're non-orientable and you're the Klein bottle. Right? So there's a clear distinction between these 2 objects, or these 2 operations. Right? But there's this notion that will capture what I just said. Right? So if you give me a surface, I can assign some number called this Euler genus. And this will be the number of crosscaps plus 2 times the number of handles that you've added to the sphere to obtain this, this new surface. Right? So what this is saying is that the sphere has Euler genus 0 because you've added nothing to it. And the projective plane has Euler genus 1 because you've only added 1 crosscap. And the torus has Euler genus 2 because you've added 1 handle, but for 1 handle, the Euler genus increases by 2. But also, the Klein bottle has Euler genus 2 because you've added 2 crosscaps. Right. So usually, I'll let gamma denote the Euler genus, and I'll let S of gamma be a surface of Euler genus gamma. Okay. So one thing to note is that if you give me some number gamma, there's going to be many, many types of surfaces. Or there's going to be many, many surfaces of that Euler genus, but there's going to be only 2 types. They're going to be orientable or non-orientable. So, for example, if you give me if you give me some number 5, then there's going to be 3, maybe 4 types, right? There's going to be one surface where you add 5 crosscaps. This will have Euler genus 5. There's going to be a surface where you add 3 crosscaps and 1 handle. This will also have Euler genus 5. And there's going to be one where you have 1 crosscap and 2 handles. This will also have Euler genus 5. Okay. So this is what a surface is, right? Okay. So now I'll start with the actual history of the topic, right? So now I'll relate this to coloring. And I'll start with what happened with planar graphs. So back in 1977, Appel and Hatkin proved that planar graphs are 4-colorable. And this is essentially saying that every planar graph is 0, 0, 0, 0 colorable, right? Because K colorability means you can partition it into K parts where each part has maximum degree 0. And Cohen, and Wodo proved that every planar graph is 2, 2, 2 colorable. Right? So instead of partitioning it into 4 parts, they were able to partition it into 3 parts where each part has a maximum degree at most 2. So each part is a subgraph of a cycle. So it's cycles or paths. Right? And then Eaton and Hall and independently Shkrekovsky, they've constructed a graph that's not 1KL colorable. Right? So what this result is saying, in this result of Cohen, and Wodo, they basically prove this is sharp. Because you cannot decrease any one of these 2's into 1's. Right? And this is one such example. Right? So I'll quickly explain why this is. Right? So here you have 2 vertices x and y, and they are adjacent. And you have many, many copies of P3s in the middle, paths of length 2. And you join all of these paths into the 2 vertices x and y. And now I claim you cannot color x and y with KL or LK. Right? Why is that? Because if you have many, many copies of this P3, then there's going to exist one copy where you cannot color any of the vertices on this P3 with color K or L. Because this vertex, if X is colored with K, then it can only be adjacent to at most K vertices colored K. And this vertex Y, if it's colored with L, then it can only be adjacent to at most L vertices colored with L. So if you have K plus L plus 1 copies of P3s in the middle, then of course one of these copies cannot have vertices of color K or L. And so at that point, all 3 vertices will need to be colored with the color 1, and the central vertex has degree 2. Right. So this shows you cannot color x and y with K and L. So I'm going to represent this as a dotted line. And I'm going to go into this graph. So this graph is saying you have some cycle, and you have a vertex in the middle. So it looks like a wheel. But instead of just having an edge here, I'm going to put some copy of this dotted line here. Right? So I'm going to replace all of these with this. Right? And then what's my claim? My claim is that this central vertex must be colored with 1. Right? So if this central vertex is not colored with 1, maybe let's say it's K, then because of this lemma, or this construction, or what I just explained here, none of these neighbors on the rim, on the cycle, can be colored with L. So all the vertices on the cycle is colored with either K or L. But since this vertex can only be adjacent to at most K vertices colored L, you'll have the same thing. If this cycle is sufficiently long, you'll have some sequence of vertices where they're not all colored with K nor L. So they will all have to be colored with 1. So this is another contradiction. So this shows that this central vertex Z must be colored with 1. And now I'll just represent this as this loop. And now I'll just have a triangle like this, right? So and this finishes the proof, because now not all 3 vertices can be colored with 1, so one of them must be K or L, and this is a contradiction. Right? Okay, so this is one example, and this actually solves the question of partitioning planar graphs into at least 3 parts. Right? So if you partition planar graphs into 4 or more parts, we know by this 4-color theorem you can make all of the maximum degrees of each part at most 0. And if it's 3 parts, then it has to be 2, 2, 2. And this is sharp because you cannot decrease this 2 into 1. So if you give me a planar graph and you improper color it with at least 3 parts, this problem is solved.
Is this planar or?
Yes, this is planar. Because so I can convince you that this and this are the same, but this I can redraw it like this, right? I can just have a cycle and have the vertex outside of this cycle and have it all adjacent in this way, right? And then it's like this, right? Yes. Okay. So now I want to go into what happened if you partition it into 2 parts, right? And this is where something bad happens, is that these people were able to construct, if you give me any pair of 2 numbers, then I can give you a planar graph that's not this D1, D2 colorable. Right? So this also solves the question, but this is something we don't like because it's just a very negative answer. And this is one construction of how to make it, but I'll skip the proof of it. So what you want to do, you want to go into sparser graphs. You want to obtain some positive results. And since planar graphs are, in some sense, a representative of sparse graphs, maybe if you make this planar graph even sparser, you can obtain some positive results. So we'll consider this girth condition, right? Because if the girth is the length of the shortest cycle, if the length of the shortest cycle is big, then your graph is sparse, right? It gets sparser and sparser as the girth gets higher and higher, right? So now you can ask these 2 questions, right? You can say, so the first one is, if you give me one pair of 2 numbers, then I want to give you the minimum girth condition so that it guarantees that every planar graph with this girth is D1, D2 colorable, where these 2 numbers are the 2 numbers you gave me. And then the second question is kind of similar, right? The second question is, you can give me some prescribed girth and one number D1, and then I can try to figure out the minimum D2 such that it guarantees that every planar graph that has girth at least the number you gave me is D1, D2 colorable, right? So this D1 is something you gave me, and this D2 is what I'll split out to you. But with these conditions, it shows that you don't really need to be planar, right? Because up here I said if we want to consider sparse graphs. So maybe the third type of question is that you can just drop this planarity condition at all, right? So you'll just ignore the planarity condition and you'll go into this realm of maximum average degree, right? And there's this nice corollary or this nice connection between planar graphs with a girth condition and the maximum average degree, right? So it says if you're planar and you have some girth g, or at least g, then your maximum average degree is bounded by this function in girth. Right? So now I've gave you 3 problems, but I won't. And there's been a lot of research done about the first, second, and third one. But today I won't talk about the second one and the third one. I'll just talk about this first one, right? So the first one is if you give me 2 numbers, I want to figure out the minimum girth such that it's colorable with these 2 numbers. Right? Okay, so this is the problem, right? So, okay. So now there are these 2 constructions that we know. Right? So the first one is I can actually make the non-D1, D2 planar graph girth 4. So I can forbid triangles, right? So this says if you give me any D1, D2, then this value, this girth value, must be at least 5. Because I can make a planar graph with girth 4 such that it's not D1, D2 colorable. And furthermore, if you give me some 2 numbers where one of them is 0, so if you give me something that's 0 and k, then I can even make it sparser. I can even make it girth 6. So this says if you give me something 0, and something, then this minimum girth g must be at least 7, right? And now what I'm going to do is I'm going to create this table, right? So I have this table, right? So the column is D1, the rows are D2, and the entries here is the minimum girth, right? So the first result is by Shkrekovsky, and he proved that if you give me dd, so if the two numbers are the same, then this girth condition is exactly 5, right? So because of the construction I showed you, we know that it has to be at least 5. So he basically showed an upper bound. He showed that if you give me a planar graph with girth 5, then I can dd color it if d is big enough, namely at least 4. Right? So I can put 5 and 5 here. Right? But something that's interesting, or something that follows from this result, is if you give me some number 5 here in a column, then everything below it is also going to be 5. Right? Because if you prove that planar graphs with girth 5 is 4, 4 colorable, then of course it's going to be 5, 4 colorable and 6, 4 colorable. Because you're just allowing larger girth. I mean, you're just allowing larger maximum degree. Right? And it's also same row-wise, right? So if you prove that planar graphs with girth 5 are 4, 6 colorable, of course it's going to be 5, 6 colorable as well because you're allowing larger and larger maximum degree, right? So once you fix some value in this table that is 5, or blue, then everything below it and everything to the right of it will also be blue, and it will be determined to be 5. Right? So this is what Shklerkovsky solved. And afterwards, Borodin and my advisor, Sasha Kostochka, they had this nice paper where they determined infinitely many values of this table. So they were able to prove that 2, 6 is 5. So this 2 is 2, 6, so this entry is 5. And because what I just said, everything to the right of it is also going to be 5. And then what else? Right? And then we want to focus on this column, the first column. Right? And there was this result. So Borodin and Kostochka, in a series of papers, series of 2 papers, and also Montassier and Oshem, they were able to determine the values of 0, 2 and 0, 4, everything. So these 2 values are still unknown, or were unknown. And this was the state of the art of the question when I got to know this problem. So how did I get to know this problem? So, so there was effort to determine this 0, 1 because it's the smallest value that we want to figure out. So it started out with 16, 14, that's a typo, that should be 12. And there was a lower bound of 10. So they constructed a planar graph with girth 9. That's not 0, 1 colorable. And then Kim, Kostochka, and Zhu, they were able to prove that it's at most 11. So this value, the girth condition that guarantees that a planar graph is 0, 1 colorable, it's either 10 or 11. And this one is still open. And there are many other values that were researched, but none of these values were determined when I got to know this problem. So now I can start the story of how I got into this problem. So André Raspo, he was visiting the University of Illinois when I was a student in 2013. And Sasha, so he was visiting my advisor, Sasha. And Sasha told André to introduce a lot of conjectures for students so students can start research. Right? So he basically whipped out this table and he said, okay, determine any of these values. So you have some infinite number of problems here. And what he was interested in particular is he said, okay, you look here, this value that's upmost in this column. So this is 4, 4. And you also look at this value here, 5. So this is 2, 6. So somehow 4 plus 4 equals 2 plus 6. So he highly suspected that this value should also be 5. Because 3 plus 5 equals 4 plus 4 and 2 plus 6. So they're all 8. Right? So he asked this question. If you give me a planar graph with girth at least 5, is it indeed D1, D2 colorable where the sum is at least 8? And then Montassier, who's a student of André, so they also asked this question, right? So this column here, none of the values were determined, right? The first 3 values are either 6 or 7, and every value here is either 5 or 6. And over here on this side of the table, you see many, many 5s, right? So they also suspected that, come on, there has to be at least one value here that's 5. Right? So they asked if this was true. So this is what I did, right? So Andre, when he was there, I worked with him, and I was not able to solve this problem. And of course, the day after he leaves, I came up with a proof. Right? So I solved this. So I sent him this paper, and we were able to extend this blue 5 one column up. So we were able to prove that if you give me a planar graph with girth at least 5, then it's going to be 3, 5 colorable. And so this work was done in 2013, but it was published in 15. So, and then I graduated, I came to KAIST, and then I met these students, and then I introduced them to this problem. And then we were able to determine one of the unknown values here. So we answered the question of Muntasir and Oshem, right? We said G of 110 is 5. So this says if you give me a planar graph with girth 5, then it's 110 colorable, right? So now this table looks like this, right? We know that there exists some value here, that's 5, and everything below is also 5, right? So what this is saying is now there's only finitely many values of this table that's left to be determined. But not only this, we looked at this paper, and we were looking into our own proof. And then we said we can do slightly better. We can do even more, right? We can generalize this to graphs on all surfaces, right? So if you give me a graph on some surface that's embeddable on some Euler genus gamma, and of course it's girth 5, then you can color it in such a way that it's 1, comma, some function that depends on gamma, and the dependency is linear in gamma, right? So here, if you stick with planar, then it's 110. But if you generalize this to higher surfaces, then it's going to be 1, comma, something that's linear in the function of your Euler genus gamma. And this is tight. So we were able to actually construct some graph. So we were able to construct a graph that's embeddable on a surface of Euler genus gamma that has girth 5. And it's not 1, comma, gamma genus, gamma colorable, where this function is linear in gamma, right? So of course it's not tight. I mean, it's not tight in the sense that the constants match exactly, but the growth rate is correct. So this growth rate, the function here that we have, the fact that it's linear in gamma, we were able to prove or come up with the construction that's tight. Right? Okay. And I have the tightness example here, but I don't have time, so I'll skip it. So after this, I was invited to come to France, and I met Louis Espere, and he was also interested in this problem, and he likes graphs on surfaces. So we worked on this topic for graphs on surfaces, right? So not planar graphs, but for any graph that's embeddable on some surface of Euler genus gamma, right? And this is, just in case you forgot, this is a notation I'll use. So this is this is one of the earlier slides. So this fact that every planar graph is 4 colorable and every planar graph is 2, 2, 2 colorable, this is the same as saying every graph on some surface of Euler genus 0 satisfies these two colorability conditions. But not only this, in their paper, but in Cohen and Wodo in this paper, they proved that if you give me a surface of Euler genus gamma, then you can partition it into 4 parts such that each part is some function of your Euler genus. And this function is linear. And he made this conjecture. They made this conjecture saying not only for 4 parts, you should be able to do it for 3 parts. And there was a series of results, right? So immediately after they made this conjecture, so 1 year after, somebody solved it. So when they solved it, he solved it with some function that's linear in gamma. And then 10 years later, they improved this to something in the square root of gamma. And then recently, Wodo just improved the constant, right? So this is the result. So this is the best known result of this conjecture by Cohen and Wodo. So what do? We generalize these results to graphs on surfaces of Euler genus gamma. Right? So what we did is we looked at this result by Appel and Hacken that said planar graphs are 4 colorable. And we said we can generalize this in some sense. Right? So we can partition graphs on surfaces into 4 parts, such that 3 of the parts are independent sets, and the last one is, the last one you can bound the maximum degree by some function of gamma. And we do the same thing for this result that says planar graphs are 2 to 2 colorable. Right? We say if you give me a graph that's embeddable on some surface of Euler genus gamma, then we can also partition it into 3 parts, where 2 parts are pads and cycles, where the maximum degree is at most 0, and the last part, the third part, is the same function in gamma, so it's linear. Right? So these 2 results are generalizations of these 2 results. And moreover, we come up with constructions that these are tight. So we say if you want to partition it into 4 parts, where 3 of them are independent, then the last part, it has to be some linear function in gamma. You cannot do better. You cannot have a sublinear function in gamma. And if you want to partition your graph into 3 parts, where the first 2 parts are pads and cycles, then the third part must be some linear function in gamma. Right? So you cannot have a sublinear function. And because of this result that says there exists a planar graph that's not 1 KL, you cannot improve this 2 into 1. Right? You cannot lower these constants. Right? So this also solves improper coloring graphs on these surfaces, right? With at least 3 parts, right? Well, I mean, it's also solved in some sense for 2 parts, because for 2 parts, you have a graph that's not JK colorable, if you give me this J and L, right? But of course, we were greedy, and we wanted to do more. So we looked into even sparser graphs, right? So what do you do if you want to look into sparser graphs? The theme is you look at the girth, right? So you have this girth condition. So, okay, what happens if you forbid triangles, if your girth is at least 4? Right? So we know you have this, this construction, what I just said. We can enforce this to not have triangles. So there exists some D1, D2 non-colorable planar graph with girth 4. So you can't have some result where you partition into 2 parts. Right? But maybe you can partition into 3 parts, right? So there's this theorem by Groch that says if you give me a triangle-free planar graph, if you partition a planar graph into 3, if you partition a triangle-free planar graph into 3 parts, then I can make them all into independent sets. Okay, so this is saying if you give me a graph on some surface of Euler genus 0, then it's 0, 0, 0 colorable. And we also generalize this results for all surfaces. Right? So we say if you give me a graph of Euler genus gamma, then I can partition it, that's triangle free. Then I can partition it into 3 parts, where 2 of them are independent. And the last one is some linear function in gamma. Right? So this is a generalization of Groch's theorem into higher surfaces. And we also show that this is tight. Right? So if you give me, so we can construct triangle-free graphs that are embeddable on some surface of Euler genus gamma. And and you want to partition it into 3 parts, and if 2 parts are required to be independent sets, then the third part must be some linear function in gamma. So you cannot lower this linear function into something that's sublinear. And this completely solves the question for triangle-free graphs, right? So for triangle-free graphs, you cannot partition into 2 parts, but you can partition into 3 parts where the first 2 are independent and the third one cannot be sublinear.
But you might also consider the problem where all these numbers are equal, C, C, C.
Yes. So I'll talk about that later as well. So we only considered determining the lexicographically smallest tuple. So now we go on to girth 5. So for girth 5, we had this result with students here, right? We proved that if you give me a graph on this surface with girth 5, then it's 1 comma some linear function. And then we said that this was tight. So you might wonder, if we can lower this 1 into 0, right? Because we're interested in this lexicographically smallest tuple. Right? But if you recall, maybe you don't because I just swept it under the rug, there's this graph that shows that it's not 0k colorable, and it's planar. But this one is even girth 6, right? So even if you allow girth 5, this will still be your counterexample, right? So there's no hope in getting this this 1 down to 0, right? And this is the same for girth 6. So if you go to girth 6, you still have this non-0k colorable planar graph, and you can embed this on any surface of Euler genus gamma. And because girth 6 is also girth 5, then you know it's something linear in gamma colorable, right? So the situation with girth 5 and girth 6 does not change. So okay, what do you do? Now you go up to girth 7. So now you go to girth 7, and we finally prove that if you give me a graph that's girth 7 on some Euler genus gamma surface, then we can partition it into 2 parts, where if one part is forced to be independent, then the other part must be linear in gamma. But so first we stopped here because everything before was linear, and here we got something that's linear, so we were happy. But then we couldn't get the tightness result, right? We couldn't come up with the graph that required this function to be something linear. So we said, okay, maybe we can improve this, and that's exactly what we did. So for this case, so once you jump from girth 6 to girth 7, now you no longer require something that's linear in gamma. You can have something that's the square root of gamma. So this is now getting close to the maximum chromatic number of the graph on surface of Euler genus gamma. So if you give me so for all graphs that are embeddable on this surface of Euler genus gamma, the maximum chromatic number grows something like the square root of gamma. It's the size of the complete graph. Right? So we got this result, and then we were able to come up with some construction that this is indeed tight. So if you give me girth 7 and 2 parts, and 1 part is independent, then you must have something that's the square root of gamma. You cannot do better. Right? So this basically solves every situation for all the girth conditions. Right? So this is solved. So this is a giant recap of what happened. Right? So if you have no constraints on the girth condition, then you can partition into 4 parts and something here that's linear, and this is required. You cannot have something sublinear. And if you want to partition into 3 parts, then you can have 2, 2, but now this thing is required to be linear. And you cannot decrease any of these 2's to 1 because of this example. And if you jump to girth 4, then I can decrease the 2 2's into 0's. And if you jump to 5, I can now decrease into 2 parts, but one of these parts must be 1. You cannot decrease to 0. And now, interestingly, the jump from girth 5 to girth 6 is nothing. There's nothing new happens between girth 5 and girth 6. But if you jump from girth 6 to girth 7, now you can decrease this 1 to 0. But not only this, you can also decrease this from something that's linear in gamma to something that's square root in gamma. Right? So there's definitely something going on between girth 6 and 7, but not 5 and 6 in terms of this improper coloring. Right? So you might wonder what happens for higher girth, right? So what's the dependency of this girth condition and this last function here, right? So we were actually able to prove this as well, right? So if you give me a graph on some surface of Euler genus gamma, and you give me some girth condition, then this function, then of course I can partition it into 2 parts and enforce one of the parts to be an independent set. But the second part, we not only know that it grows something like square root of gamma, we know it grows in something that's square root of gamma over L, right? So this is something natural. If your girth is bigger and bigger, your graph is sparser and sparser. So you should be able to color it easier and easier, right? And the dependency is the inverse of the square root of your girth, right? Okay. Any questions? I've like thrown you like so many different results. Yes?
So did you try for small gamma? Actually, what we start is a planar graph. So we
Yes.
in girls 5, the formulation is maximum of 10 and the function.
Yes.
But in other girls, did you try for small gamma?
No.
How did you prove those things?
So I'll talk about the proof as well. Yes.
Based on what we did for the
Yes and no.
How big is the constant hidden in the big O?
In the big O,
Yeah.
it's definitely smaller than this. But it's, I mean, you can calculate it, but it's not pretty. So it's something ugly that I don't want to. I didn't want to simplify and put
It's
here.
not 10 to the 10.
It's not 10 to the 10.
Okay.
It's like less than 1,000. Okay, so now I'll talk about the proofs. So the first two results that don't have these girth constraints, we use this lemma, right? So what this lemma says is you fix some surface and you can pick any vertex you like. Then I can find some connected subgraph that contains this vertex, and I will contract this connected subgraph. And what happens if you contract? Then the entire graph will turn planar. And then I can apply the four-color theorem, and then I will just use the fourth color on this connected component. But then but then you cannot control the maximum degree of this fourth color. So what I'll do is I'll solve something stronger that says every vertex of this graph has some linear in gamma number of neighbors in this component that you've contracted. So after you have this lemma, these two results just the first one follows from the four-color theorem, and the second one follows from the fact that planar graphs are 2-to-2 colorable. And this lemma is like a 2-page, some double induction thing, where you find a non-contractible cycle, you cut the surface, and you lower the genus, you do some clever tricks, and you combine the connected subgraphs together, and then so it's just basic induction, but maybe basic is too naive of a word.
So probably you make H to be induced subgraph? With this lemma, you don't...
We don't care.
Yeah, but it's okay to assume.
Yes. So, but the thing is, once you find this non-contractible cycle, if you cut your surface, you end up in different situations, right? Maybe you cut the surface and you have two orientable surfaces. Maybe you cut the surface and you end up with one non-orientable surface and one orientable surface. Maybe you cut the surface and the genus drops down, but you're still one surface. Maybe this cycle was not separating, maybe it was separating. So you have different cases you have to take care of. Right?
So non-contractible in a topological sense.
So we cut the graph onto a graph cycle, but non-contractible in the topological sense. Yes. Yeah. So a non-contractible cycle in graph theory sense is the same as the topological curve sense. Yes. It's non-contractible if the inside is not homeomorphic to a disk. When you ignore everything inside, if you ignore all the vertices and edges inside. So you grab a cycle, and everything inside you just remove, and if this is homeomorphic to a disk, then this is contractible. If it's not homeomorphic to a disk, it's non-contractible. Okay. Okay, and so this is how you prove the first two results with no constraints. And now you have this result and this result and this result that all have constraints. So this one, we use discharging. But this one, this result that says girth 5 is 1 something linear in gamma, it uses discharging, but we had to use the fact that you have some vertices of high charge left over. Okay. So over here and here we use something similar, but we say, okay, you have some leftover charge here or there, so we have some different cases to consider. And the proof of this easily generalizes to the proof of this one. Right? And this one I'll actually talk about more in the open problem section. So now I'll talk about the open problems, right? So this is the same, right? So for planar graphs, you have this many open problems, right? Everything blue is determined, but everything black is not determined. So you can go ahead and try to figure out which one is 5 or 6, or 6 or 7, or 7 or 8, right? So of course the biggest question in this area is trying to determine G of 0, 1, right? Because somehow 0, 1 is the smallest number, so it's the most natural question. And a lot of people have tried to determine it, but we still don't know if the answer is 10 or 11. Okay. And the second question is this jump thing, right? So if you look at this column, you have 7s, and this is 7 or 8, and now this is 8. So that's somehow continuous. But now you jump to either 10 or 11. So there's definitely a jump going on here. And everywhere else, it seems natural, but maybe there's a second jump here, right? Maybe. Maybe this is all 5, and then maybe it jumps to 7. Right? So if this jump happens, this will be very surprising, right? I doubt that there's this jump. And now I have some open questions for graphs on surfaces, right? So the first one is what Hojin and Jisoo were asking about small genus, right? So Cohen, Goddard, and Jesurum, they proved graphs on a torus. You can partition it into 5 parts where each part is an induced matching, so 5 ones. And they also solved that it's 2, 2, 2. So planar graphs were 2, 2, 2, but they extended this to graphs on a torus. So graphs on toruses are also 2, 2, 2 colorable. But they don't know if every toroidal graph is 1, 1, 1, 1 colorable, right? So they don't know, so they explicitly ask if you want to partition your graph into subgraphs of this induced matchings, can you do it with 4 parts instead of 5? Right? So this question they don't know. So now I'll talk about higher genus, so general gamma, right? So we were able to prove that if you do 4 parts, we can force 3 of them to be independent. And the second result is some constant, and then something linear in gamma. And then Wodo proved if you don't have any constants, then he can do square root of gamma, square root of gamma, square root of gamma. And we looked at his proof, and you can actually do something that looks like 9, and then square root of gamma, square root of gamma. So you cannot do constant, but you can do constant, sublinear, and you can do constant, linear, and you can do square root. So the question is, can you decrease this 9 into this 2? Right? Because then it will be best possible. Because we know since there exists this planar graph that's not 1 KL colorable, you cannot decrease this 2 into 1. So this will be also a tight result in some sense. But of course this function f in gamma has to be sublinear, because if it's not sublinear, then it just gets eaten by this result. Okay. So this is one question. So the second question is, so this is what we talked about. So this is just, so I said I'll be talking about this. So, and I said this is just an easy consequence of the proof when L is 7. So I said we prove this result when girth is at least 7, and then we just generalize this to all girth. But then we think this dependency on this L, right, this girth condition, this inverse square root is somehow too weak. Right? We think maybe, so if the girth gets bigger, then the constant or the growth rate that depends on L should be much faster, much faster. Right? So we conjecture that there's going to be some function in L, in this girth condition, that goes to 0, of course, as L goes to infinity, such that your graph on your surface with this girth condition will be 0, comma, something gamma to this power of this function. Right? So here, this power is something like a half. Right? So it's gamma to a half. But here we say maybe this dependency on L should be in the exponent. And there's no way it could be this. This can't be the correct the growth rate of it, right? And so one evidence is this result by Gimbel and Thomason, right? So okay, if your graph is 0k colorable, right, then this implies your graph is k plus 2 colorable in the usual proper coloring sense, because the first part you will just use one color, and the second part has a maximum degree k, so you can just color it with k plus 1 colors. So you have some k plus 2 coloring. And you consider the contrapositive, right? You say, okay, so if your graph is not k plus 2 colorable, then you're not 0k colorable. And this is what Gimbel and Thomason proved. They proved that under these some conditions, there exists a graph on a surface of Euler genus gamma that has some girth, and it's not something colorable, where C is just a constant, and this is gamma to some power of 1 over 2L plus 2. Right? So this function that depends on your girth must be at least this. The growth rate must be at least this. Right? And that's it. So these are all the people. Right? This is us. That's me and the 3 students solving the question while watching the World Cup finals in 2014. And this is Louis Espere, André Raspo, Mikhail Montassier, and Pascal Lochev.